Good morning. Today we will start with the entropy. We introduced the second law of thermodynamics in the previous chapter. We apply the second law to process. The first law of thermodynamics deals with the property energy and conservation of it. The second law leads to the definition of new property called entropy. Entropy is a somewhat abstract property and it is difficult to give a physical description of what without considering the microscopic state of the system. Entropy is best understood and appreciated by studying its use in commonly encountered engineering processes. So this chapter we will apply the second law of thermodynamics to process, define a new property called entropy to quantify the second law effects, establish the increase of entropy principle, calculate the entropy changes that take place during process for pure substance, incompressible substance and ideal gases, examine a special case of idealized process called isotropic process and develop the property relations for these processes, derive the reversible steady flow work relations, develop the isotropic efficiencies for various steady flow devices, introduce and apply the entropy balance to various systems. So first we will start with the concept of entropy. The second law of thermodynamics often leads to expressions that involve inequalities. An irreversible, it means actual heat engine, for example, is less efficient than a reversible one operating between the same two thermal energy reservoirs. Likewise, an inversible refrigerator or a heat pump has a lower coefficient of performance than a reversible one operating between the same temperature limits. Another important inequality that has major consequences in thermodynamics is Clausius inequality. So it was first stated by German physicist Clausius, one of the founders of thermodynamics, and it is expressed as that the cyclic integral of del Q by del T is always less than or equal to 0. This inequality is valid for cycles whether it is reversible or irreversible. The symbol cyclic integral with the circle in the middle is used to indicate that the integration is to be performed over the entire cycle. Any heat transfer to or from the system can be considered to consist of differential amounts of heat transfer. Then the cycle integral of del Q by T can be viewed as the sum of all these differential amounts of heat transfer divided by the temperature at the boundary. To demonstrate the validity of Clausius inequality, consider a system connected to a thermal energy reservoir as at a constant thermodynamic absolute temperature Tr. So this is your thermal energy reservoir Tr. The cyclic device receives QR amount of heat from reservoir and supplies this heat to a system whose temperature at the part of the boundary is T. So it will supply after the work output, this heat is supplied to this system. While producing work del reversible here and this system produce work del W system as a result of this heat transfer. Now apply this energy balance to combined system, identify this dotted lines. So we will apply this energy balance to this system. So what we have here, that is total combined work. So this is the shaft work produced by this reversible cycle and this is the work produced by this system. So combined work is equal to, written in terms of, is equal to del QR minus DEC, where del WC is the total work combined system, means this work plus this work. So del WC is equal to this combined work of reversible cycle and system, and del DEC is the change in the total energy of the combined system. So DEC is here change in total energy of the combined system. Considering the cycle device is reversible one, we have, now suppose this cycle, or you can say this combined cycle is reversible, and for reversible cycle this is the condition. So for this reversible cycle it is del QR by Tr is equal to del Q by T, where the sign del T is determined with respect to system positive if the system positive if to the system and negative if from the system, and the sign del QR is determined with respect to the reversible cyclic device eliminating del QR from the two relations verb. So you can replace this del QR, you can say in terms of del Q. So you can replace this del QR and the expressions become del WC is equal to TR del Q by T minus DEC. The cyclic integral of energy, the net change in energy, which is a property during a cycle, is 0. Means if you take integral of this part, it is 0. Here WC is cyclic integral of this del W, which is TR, which is constant. So integral is of del Q by T. Now in this diagram you can observe this one thing, that this system is working, this cycle is working by taking heat from only one thermal reservoir, and there is no second you can say thermal reservoir or heat sink, which is you can say violation of the Kelvin-Planck statement of second law, which states that no system can produce a net amount of work while operating in a cycle and exchanging heat with a single thermal energy reservoir, which means for the work to produce and cycle to operate, there must be two thermal energy reservoir. One is at high temperature, second is at low temperature. So that so it means WC cannot be the work output, and thus it cannot be a positive quantity. Means the work which is reflected here, it should not be there. It is not a positive quantity. It should be a negative quantity, or it should not be there. So if your work should be, WC should be negative quantity. As we know, it is dependent on TR and cyclic integral of del Q by T. Temperature can't be negative. It is always positive if you take temperature in terms of Kelvin, because we had considered here temperature in terms of Kelvin. So temperature can't be negative. It means this quantity left, which is cyclic integral of del Q by T, is negative. Considering that TR is a thermodynamic temperature and thus a positive quantity, we must have this condition that cyclic integral of del Q by T is less than or equal to 0, which is Clausius inequality, and this is called Clausius inequality. This inequality is valid for all thermodynamic cycles, reversible or irreversible, including the refrigeration cycle. If no irreversibilities occur within the system as well as the reversible cycle device, then the cycle undergone by the combined system is internally reversible. As such, it can be reversed. In the reverse cycle case, all the quantities have the same magnitude but the opposite sign. Therefore, the work WC, which could not be positive quantity in a regular case, cannot be a negative quantity in reverse case. Then it follows that WC is equal to 0 for you can say reversible, since it cannot be a positive or negative quantity, and therefore for internally reversible cycle, del Q, cyclic integral of del Q by T is equal to 0. Thus we conclude that the equality in the Clausius inequality holds for totally or just internally reversible cycles, and the equality for the irreversible ones. Now we had this relation, which is your Clausius inequality, that the cyclic integral of a change in del Q by T is equal to 0. Take another example. Take this example of piston and cylinder. Here you can see after 1, 2nd and 3rd process, the initial condition volume is suppose 1 meter cube, then volume has increased from 1 meter cube to 3 meter cube, and then again piston has moved back to the same position and volume has decreased to 1 meter cube. So for this process, the cyclic integral of volume is equal to 0, means because the volume has returned to its original position. So when the piston returns to initial position at the end of cycle, the volume of gas also returns to initial position. Thus the net change in volume during a cycle is 0. This is also expressed as the integral, cyclic integral of volume is 0. Change in volume is 0. That is, the cyclic integral of volume or any property is 0. Conversely, a quantity whose cyclic integral is 0 depends on state only and not the process path. Means if cyclic integral of change in volume is 0, means it depends only on the initial state and final state. It does not depend on the what path you have to follow to achieve from this state to this state. Therefore, the quantity del Q by T must represent a property in differential form. And we know that volume is the property of the system. So same here, you can see here, if you compare this quantity, change in volume, with this quantity, both cycle integral is 0. It means this quantity is also a property of system. So this is the new thing. Therefore, the quantity del Q by T reversible must represent a property in differential form. Clausius realized in 1865 that he had discovered a new thermodynamic property, and he chose to name this property as entropy. It is designated S and is defined by, so this entropy is designated by ds is equal to del Q by T for reversible. Entropy is an extensive property of a system, and sometimes it is referred to as total entropy. Entropy per unit mass, designated S, is an intensive property and has a unit of kilojoule per kilogram. The term entropy is generally used to refer to both total entropy and entropy per unit mass, since the context usually clarifies which one is meant. The entropy change of system during a process can be determined by integrating. So this is S2 minus S1. This is change in entropy. If you integrate the del Q by T, we will get change in the entropy. But engineers are not concerned with the absolute value of entropy. Means we need only change in the entropy. Engineers are usually concerned with the change in entropy. Therefore, the entropy of substance can be assigned a zero value at some arbitrarily selected reference state, and the entropy values at other states can be determined. To perform the integration in equation, this one needs to know the relation between Q and T during a process. This relation is often not available, and the integral can be performed for a few cases only. For the majority of cases, we have to rely on tabulated data for entropy. Suppose if there is a process from 1 to 2, so we have to just find out what is the entropy at 2 and what is entropy at 1. We want del S, change in entropy. If the process is a reversible process, or whether it is a reversible process, the change in entropy is same, because entropy is your property of the system. It is a dot depend on path. Therefore, the entropy change del S between two specific states is same no matter what path, reversible or reversible. Whatever you path will follow, 1 to 2 reversible or reversible, the change in entropy is same for both the paths. Also note that the integral gives us the value of entropy change only if integration is carried along an internally reversible path between two states. The integral del Q by T along an irreversible path is not a property, and in general different values will be obtained when the integration is carried out along different irreversible paths. Therefore, even for irreversible process, the entropy change should be determined by carrying out this integration along some convenient imaginary internally reversible path between the specified states. A special case, internally reversible isothermal heat transfer process. Recall that isothermal heat transfer processes are internally reversible. Therefore, the entropy change of a system during an internally reversible isothermal heat transfer process can be determined by performing the integration. So if you take the integration from 1 to 2 del Q by T, now if the process is isothermal, this temperature remains constant T0. So if it is constant, you can take out of integration. So del SQ becomes 1 by T0, integration 1 to 2 del Q internally reversible, which reduces to del S is equal to Q by T0, where T0 is constant temperature of system and Q is heat transfer from internally reversible process. Equation 7.6 is particularly useful for determining the entropy changes of thermal energy reservoirs that can absorb or supply heat indefinitely at constant temperature. Means this relation, which is del Q S is equal to Q by 2, because thermal reservoir has constant temperature and they can provide infinite amount of heat. So this relation can be used for thermal energy reservoir. Notice that the entropy change of system during internally reversible isothermal process can be positive or negative depending on the direction of heat transfer. Heat transfer system increases the entropy of the system, whereas heat transfer from a system decreases. In fact, losing heat is the only way the entropy of system can be decreased. So this is up to here about the entropy. So like this video, subscribe this channel, and thank you for watching this video.